Have you ever looked at the world of chemistry, with its millions and millions of different molecules, and just wondered, how on earth do we keep track of it all? Well, it's a lot like learning a language, and today we're going to start with the absolute basics, the alphabet if you will. We're diving into alkanes. They're the simplest, most fundamental family in all of organic chemistry. Let's get into it.
So, here's our game plan. First, we'll get properly introduced to the alkanes. Then, we're going to crack the code of how we name them. It's a system, and it's pretty clever. After that, we'll see what happens when they form circles, and we'll explore their unique physical properties, kind of like their personalities. We'll look at what they actually do in chemical reactions, and we'll finish up with a really fascinating idea, how you can use the exact same parts to build totally different molecules.
All right, let's jump right in. First up, meeting the alkanes. You should think of these as the absolute ground floor of organic chemistry. They are the simplest family of molecules out there, and they form the foundation for pretty much everything else.
So, what is an alkane really? Well, at its heart, it's a hydrocarbon, which just means it's made of only hydrogen and carbon atoms. But here's the crucial rule. The one thing that makes an alkane, it only has single bonds between its carbon atoms. No double bonds, no triple bonds, just simple, single connections. They are the basic Lego bricks of chemistry, forming the backbone for an absolutely staggering number of more complex molecules.
Okay, with millions of possible molecules, how do we avoid total chaos? How do we make sure a chemist in Tokyo and a chemist in Toronto are talking about the exact same thing? We need a universal system. And that's where IUPAC, the International Union of Pure and Applied Chemistry, comes to the rescue. They created this brilliant set of rules that gives every single organic molecule its own unique, unambiguous name.
And the process is actually just a logical, four-step recipe. First, you find the parent. That's the longest, continuous chain of carbons you can find. This gives the molecule its last name. Then, you number that chain, kind of like giving each carbon an address, and you always start from the end that's closest to any branches. Step 3, you identify what those branches are. We call them substituents, and you note their address. And finally, you put all those pieces together to build one complete, unique name.
Look, theory is one thing, but let's see how this actually works in practice. We're going to take this molecule here, and over the next few slides, we're going to break it down step by step to figure out its unique IUPAC name. Why don't you try to follow along and see if you can figure it out with me?
Okay, step 1. Find that longest continuous carbon chain. If we trace a path through the molecule, the longest one we can find has 9 carbons in it. In chemistry speak, the prefix for 9 is non, and since it's an alkane, we add the ane ending. So, the parent name, the last name is nonane. See? Not so bad.
Now for the next part, numbering the chain and naming the branches. Remember the rule. We start from the end that gives those branches, the substituents, the lowest possible numbers. If we start from the right, our first branch is on carbon number 2. If we started from the left, it wouldn't be until carbon 4. So we've got to start from the right. That tells us we have a chloro group on carbon 2, and then we have 2 methyl groups, one on carbon 3 and another on carbon 6.
And now for the grand finale, putting it all together. We list the substituents alphabetically, so chloro comes before methyl. And since we have 2 methyl groups, we use the prefix di to show that. So, putting all the pieces in order, we get 2-chloro-3,6-dimethyl-nonane. And just like that, we've created a totally unique ID for this specific molecule out of millions and millions of possibilities.
So far, we've been looking at chains, right? Some are straight, some are branched, but what happens when those chains loop around and the 2 ends connect, like a snake biting its own tail? Well, you get something new.
They form what we call cycloalkanes, and the naming for these is actually wonderfully simple. You just take the alkane name for the number of carbons in the ring and slap the prefix cyclo on the front. So a 6-carbon ring is cyclohexane, a 5-carbon ring, cyclopentane. It's that easy. Any branches are named and numbered just like we did with the chains a minute ago.
So now that we know what they are and how to name them, let's talk a little bit about their physical properties. And you can honestly think of these as their molecular personalities, the traits that define how they behave in the real world.
Now, what's really cool here is the clear trend you can spot just by scanning the table. Take a look at that physical state column. The little guys, methane through butane, are all gases at room temperature. But as soon as you hit pentane, with 5 carbons, boom, they become liquids. This tells us something really important. Size matters. And if you're a visual person, this chart really drives that point home. As that carbon chain gets longer, the boiling point just shoots up. Why? Well, it's because larger molecules have stronger forces holding them together.
They're stickier, you could say. So you need to crank up the heat a lot more to get enough energy to pull them apart and turn them into a gas. But it's not just about size. Shape is a huge deal too. Think about it. Long straight-chain alkanes can stack together really neatly, almost like logs. This maximizes their contact and creates strong attractions, which means higher boiling points. But branched alkanes are more lumpy. They're compact, so they can't pack together as tightly. This results in weaker forces between them and, you guessed it, lower boiling points.
And here are two other key personality traits. Alkanes are nonpolar, which is a fancy way of saying they hate water. They just won't dissolve in it. It's literally like trying to mix oil and vinegar. They're also less dense than water. And this isn't just some random trivia. This combination is the exact reason why crude oil, which is mostly a mix of alkanes, floats on the ocean's surface during a spill.
So we know what they are, we know their personalities, but what do they actually do? Let's take a quick peek at their most important chemical reactions.
Truth be told, alkanes are kinda lazy. They're not very reactive, but there are two things they do really, really well. The first one is combustion. That's just a fancy word for burning. Anytime you fire up a propane grill, you are running this exact reaction. Propane plus oxygen gives you carbon dioxide, water, and, the reason you're doing it, a whole lot of energy. The other key reaction is called halogenation, where a halogen, like chlorine, can swap places with a hydrogen atom, usually with a little nudge from some UV light.
But this swap isn't totally random. The halogen actually has a preference. It's a bit picky. It's more likely to replace a hydrogen on a carbon that's already bonded to a bunch of other carbons. This means you often end up with a major product, which is the one that forms most of the time, and a minor product. So you see, chemistry isn't just about what can happen, but also about what's likely to happen.
And that brings us to our final concept. And honestly, it's maybe the most mind-bending one of all. This idea that you can take the exact same set of atomic parts and use them to build completely different molecules. This amazing phenomenon is called isomerism. Isomers are compounds that share the exact same molecular formula, so the same parts list, the same count of each atom, but they have those atoms connected in a different way. It's like having the same Lego bricks but using a different set of instructions, giving you totally different structures with totally different properties. So let's take a simple formula. C4H10. That's 4 carbons and 10 hydrogens. Now, the most obvious, straightforward way to put these atoms together is in a simple, straight line. And when you do that, you get this molecule here, N-butane.
But you can also take those exact same 4 carbons and 10 hydrogens and arrange them in a branched structure, like this. This creates a completely different molecule called 2-methylpropane. It has a different shape, a different boiling point, different chemical properties. It is a different substance, all from the exact same atomic parts as N-butane. And this is where it gets absolutely incredible. Butane, with just 4 carbons, has only 2 isomers. But as you add more carbons, the number of possibilities just explodes. Decane, with 10 carbons, has 75 different isomers. Get this, an alkane with just 40 carbons has over 62 trillion possible isomers. So I'll leave you with this question. What does that tell us about the breathtaking, almost infinite complexity that can spring forth from just a few very simple building blocks and a handful of simple rules?